Hello. We have seen the gain coefficient and its dependence on the intracavity field. We know that we can write down the gain coefficient g of nu as the small signal gain and divided by 1 plus phi by phi saturation. Now you would recall that phi is the intracavity photon flux. You should note that this formula is indeed true for homogeneously broadened line shapes. We are talking about a field which is largely centered, is monochromatic or narrowband, largely centered at the frequency nu, right? And phi saturation gives us a measure which provides a scale for the intracavity intensity. If the intracavity intensity is comparable to the saturation intensity or saturation flux, the gain decreases by a factor of half. So this equation that we have written down here is not really completely correct. So the issue is the following, that when I'm looking at gain and its dependence on the intensity, what matters is the electromagnetic energy density within the cavity. And we know that the photon flux can be seen more clearly as arising out of a flux which is right propagating, that's towards the increasing values of z, and a photon flux that is left propagating, right? And both of these are sort of the traveling waves, if you like, which are counter propagating, and they form the total energy density which is within the cavity. And we know something very clearly, that if I have a wave, so let's say I draw my cavity and I have a wave which is traveling to the right and also have a wave which is traveling to the left, then you see that these two will interfere, and what I would get is actually the familiar standing wave pattern, right, associated with that wave, right? So you see that this particular pattern remains constant in time. You have regions of, there are nodes and then there are antinodes. In the regions of nodes, the intensity remains zero in all time, right? The field itself, the electromagnetic energy density itself is zero, whereas there is large energy density contained at the antinodes and so on. So you see that clearly there is a spatial structure which I have ignored when I write down a gain expression of this kind, which I note as equation 1. Clearly, I have ignored this spatial dependence, which is inbuilt in all standing wave cavities that typically we have for a laser. What we do now is to take account for this formation of the standing waves and see how we can capture this spatial inhomogeneity into our gain equation. You know that my intensity is proportional, or intensity is equal to the energy times the photon flux, which in turn is equivalent to energy density times the velocity with which the energy is moving, right? So this expressions you do know. So you see that I can write down the following. I can write down the energy density for a standing wave within a cavity in the following form, right? So I'm writing down the electromagnetic energy density within a cavity. And this is simply h nu by c times phi, right? And this is, we know by definition in electromagnetics, energy density is simply epsilon naught times E square, where E is the corresponding electric field associated with the electromagnetic wave. Now remember, the total energy density has got terms which are coming from the magnetic field as well as the electric field. And for the electromagnetic wave, both of these contributions are equal. Hence, the factor of half has gone from here. And this essentially is what is the electromagnetic energy density associated with the electromagnetic wave, right? And this is equal to epsilon naught. Let's look at a sort of a plane wave basis just for simplicity. I have E naught square, which is the amplitude. We have cosine omega t or cosine square omega t because we're looking at a square now, and sine square k times z. K is the propagation constant, which in this case is simply 2 pi by lambda, right? So this is the form of the electromagnetic energy density. Now, if I'm looking at an time averaged quantity, right? Time average of the photon flux, like we do for intensity. Intensity is a time averaged quantity. So this cosine square omega t, a time average will give me half. And you see that that is what now becomes my the time averaged energy density, if you like, is simply half epsilon naught E naught square sine square kz. Now let's look at it a little carefully because I want to still think of it in terms of right propagating and left propagating fields. So I write down the following, that my E is traveling in positive and negative z direction. Uh, as I said, is simply E naught. There must be some polarization. Let's not worry about it. It's cosine omega t times sine kz, right? This, I can expand this cosine times sine in the following form. So there is epsilon and this E naught by 2. Let me take that as common outside, and I can write this as sine kz minus omega t plus sine kz plus omega t. Now we can clearly identify that this quantity is essentially the E plus, which is that is electromagnetic wave that is traveling in the positive z direction, right? And similarly, this term corresponds to E minus, right? You would agree with that because this is the wave now propagating backwards. That's what I was saying, that the standing wave is a superposition or interference which arises out of the two traveling waves traveling in traveling opposite to each other or counter propagating. So this is how uh, you get the electric field. So I can write this out. This is how you identify the right and the left propagating electric fields. So I can write this out as E plus ZT plus E minus ZT, right? And absolutely similarly, now that we have constructed these, I can simply construct the energy density associated with the field traveling in the plus and minus directions, right? For example, this quantity is simply epsilon naught. Now E plus ZT, and I need to square this, right? This will give me epsilon naught, and then I will get a E naught square by a factor of 4, which is coming from the amplitude, and the sine square, when you do and you average it in time, you get a factor of half. So what you get is basically epsilon naught. This is a time averaged quantity, is simply E naught square by 8. All right, similarly, I would get E minus, where I would have changed this to E minus. And of course, I have the same relationship. Both plus and minus have the same relationship, apart from the fact that these changes in the sign, the argument in the sign is kz minus omega t, kz plus omega t. That really doesn't change the averages. So you get essentially this relationship, which is time averaged. So now if I go back and look at equation number 2 and try to write down equation number 2 in terms of utilizing equation number 3. So if I combine 2 and 3, I get the following form for the photon flux. I can write down my total phi as 2 times phi plus all these at nu, of course, plus phi minus nu times sine square kz, right? So this is what the time averaged uh, photon flux in terms of right and left propagating will give me that. You can clearly see. So if I plug these relationships back in, I would get here twice epsilon naught E naught square by 8 plus epsilon naught E naught square by 8, right? Sine square kz, which you will quickly identify as simply epsilon naught E naught square sine square kz. And you see this factor, there'll be a factor of 4 at the bottom, 2 gets cancelled, so this becomes 2, which is precisely, you see, the equation 2 that we got, right? So hence this formulation actually works. So what I'm going to do is I can write this in terms of photon flux, or I can write in terms of intensity. So my intensity, which is simply h nu times phi, right, can as well be written in a similar manner as twice I plus I minus the right and the left propagating intensity times the spatial dependence that arises from interference, right? So this is I'll either use the equation number 4 or equation number 4 prime, depending on whether I want to use intensity or the flux, right? So one can rewrite now the gain in a more honest manner that captures this as G naught of nu. Again, the caveat that this is a gain associated with the homogeneously broadened active media, and the gain saturation can be thought of as in this fashion. It is twice phi plus phi minus times sine square kz divided by the 5 nu saturation, right? That has to be kept in mind. The field which is at a frequency nu, right? So that is how the gain now transforms with this, we have put in this spatial dependence, right? Which is important. Now let us see how does that look like in space. So remember that I have now I'm drawing the z dependence of the gain. So I'm basically plotting this ratio, which is g of nu divided by g naught of nu, right? So the maximum value it takes is indeed 1. And where does the 1 happen? 1 happens when the sine square kz factors gives us a 0. So at z equal to 0, for example, I might have a form like that. This is the sine square. And this I need to plot from 0 to L. And for example, this could be the intensity for a particular, uh, for a particular level of phi, phi plus and phi minus. For a smaller intensity flux, it might be of this kind. It essentially depends on the comparative intensity between phi plus, phi minus, and phi saturation. So you clearly see that now my gain is periodically varying at the nodes, right? these are nodes, I get a small signal gain. I get very large gain, and the intensity, corresponding intensity, is zero. Whereas at the antinodes, the gain is saturated. What we obtain is what is known as the spatial hole burning. That is, in the spatial profile of the gain, one has burnt holes, you know, in the gain profile. The gain has decreased at these locations of the antinodes of the standing wave pattern, right? So remember that this gain variation is happening at the scale of lambda. So you see that, so we are looking at, these holes whenever kz is going to be, basically n times pi, right? We are going to get a hole. So essentially, these are separated at a distance of essentially, pi by k. That is a separation between the holes, right? Which you can clearly see is simply lambda by 2. So you see, at the scale of the wavelength, there is a variation in the gain, and clearly this is quite rapid. All right, so let me be careful. I have now here uh, a phi 1, let us say, uh, and there is another phi here, which is phi 2, and clearly phi 1 is larger than phi 2, right? So larger is the photon flux, greater is the depth of the hole that we have burnt in this hole profile, and uh, because this is happening rapidly in space, one can probably approximate, this to a uniform field, right, of that kind. So you see that I can write down my equation number 5, which is as the following. I can write it down as g of nu as g naught of nu, and this is 1 plus. So there was a factor of 2, and there is a sine square kz, which I'm averaging in space now, let us say, and the 2 factor gets cancelled. So what I get eventually is phi plus phi minus divided by phi nu saturation. So this expression is arising out of something called this is what we would call as a mean field approximation. That is, I am replacing the actual variation, uh, actual rapid variation of the field by a mean quantity, which is by an average quantity. So this would be called as a mean field approximation, or in other words, a uniform field approximation, right? So even though there is a inbuilt structure to the field, I am approximating it by a uniform field across the gain length. So obviously you would see that because of spatial hole burning, the gain that we were considering as arising so, right, has actually reduced from that value, it has reduced to this value, right? So you see that this variation, this reduction of the gain because of spatial hole burning is the consequence of this spatially distributed or spatially varying saturation of the gain, right? So that is something to keep in mind. So we have now focused on the internal field distribution, or inside the laser, what is the field distribution and so on. So our next interest is to look for, what is the lasing output, and how does one connect this internal field distribution optimally to the external laser output that we are interested in.